If you saw my previous video on the I2C bus, this display will look familiar, but it is actually a little bit different. This particular display is the same kind as the one I had in the previous video, except that it's now a display that's designed for the SPI serial data bus, and the previous one was designed for the I2C data bus. And what I've done is now written some code to drive this display on the SPI bus. Everything else here, the same breakout board as in the previous video, which has the accelerometer, gyroscope, and magnetometer. This is still I2C, and it still communicates to the microcontroller with I2C, but the microcontroller is now communicating to the display with SPI. So this is a video about the SPI data bus. All this stuff in here, these are a bunch of field effect MOSFET transistors, and they're used for level shifting because this board and this display run on 3.3 volts and the microcontroller is running on 5 volts. So this is how the different parts of the SPI bus are hooked together. There's 3 wires on the SPI bus, clock, and then 2 data lines. Contrary to the I2C, which only had 2 digital lines, this one has 3. In the I2C, the data line was bidirectional. It means the data could flow in either direction on that line. In this case, the data lines are unidirectional, and they can only go in one direction. It's a single master multi-slave situation again, just like the I2C. So you have one master, in this case the microcontroller, and then a bunch of slaves that are all tied together on the same data bus. How you differentiate each slave from the other is instead of sending an address along the data line, you have a separate digital line going to each of the slaves, and when you pull that line low, the slave will wake up and start to communicate on the I2C bus. And generally you only pull one of these lines low if you've got more than one slave. So when the master is sending data to the slave, it sends out a series of clock pulses, and the data comes out on the master out slave in line, MOSI, and it goes into whatever slave, or all the slaves, or however many slaves you've activated by pulling the slave select line down, or low. And the data goes out on that bus, or on that line, and into each of the slaves that are activated. When you want to read from a slave, the slaves will transmit data back out onto this master in slave out. Now just thinking about it here, I realize that you can't really have more than one slave going on at the same time because it's clocking data out. And if you've got 2 slaves clocking out different data, there's going to be a contention on the master in slave out line. There are situations where your slave devices are one direction, like this display here. I can't read from the display and I can only write to it. And so I don't have the master in slave out line connected up. It's not needed. So in this case, if I had more than one display, I could write to all the displays at the same time without worrying about a contention of the data coming out of them fighting each other. But in my situation here, there's only one SPI device, and that's the display itself. So it doesn't matter, because we're only going to be enabling one. Internally, they all look the same way. The CPU and each of the slaves will have an 8-bit shift register here, which is driven by the clock. In the case of the CPU, or the master, the clock is generated internal to the master, and it also goes out, which is what I showed you in the previous one. This is the same line here, S clock. In the case of a slave, the S clock line goes in, and there's no clock generated internally. Now, the shift register, from the perspective of the master, can be loaded from the CPU, in this case the microcontroller. You can load 8 bits at once in parallel, and then every clock pulse shifts out 1 bit. Inside the slave, you got the same thing going on. The data is coming in, but it's also shifting data back out. And so the master device is receiving data coming back from the slave in the same manner. So it's kind of a loop. The first bit that gets clocked out of here goes into the shift register in the slave, but it's going to take another 8 pulses to get it all the way through to come back out again, to come out here. So in order to get this bit here, which is shifted this direction, back around again, you're going to have to clock it 16 times. Normally you're not worried about that. You don't want to read what you've shifted out. You want to read what the slave presents to you. Data coming in to the master or the slave is assembled in the shift register, and then it can be read out in parallel. So that's basically a very simplified diagram of what is inside each of the devices. Now, the clocking scheme can take 4 different modes, and it depends on the polarity of the clock, whether it's idling high or idling low, and on what edge of the clock do you actually clock the data out and the data in. And they're called mode 1 through mode 3. And different SPI devices use different modes. I believe mode 0 is the most common, but I'm not totally sure of that. I haven't used a whole lot of SPI type devices. A particular project I worked on, I had a couple of different SPI devices in the same project, slave devices, and one of them was on mode 0 and the other one was on mode 2. And I had to switch modes in the SPI device inside the microcontroller in order to be able to communicate from one to the other. And so the data is shifted out 1 bit at a time. This just represents the data. This is where the data can change, and this is where the data is solid. And so in mode 0, the clock idles low. So when you're not clocking anything, the clock line goes down to 0. And then when you want to shift data in or out, the rising edge of the clock, indicated here, is where the data is supposed to be valid, and then it gets shifted in or out. Mode 1 down here, the clock idles low again, but this time the clock falling edge, the clock's falling edge is where the data is shifted in or out. And similarly for mode 2, the clock idles high, falling edge. Mode 3, the clock idles, clock idles high, and it's the rising edge. I don't know why there's all these different modes, but they do exist, and you have to look at the data sheet for the device that you're playing with and figure out which mode it is. If it doesn't work, just rewrite your code for a different mode and see what happens, and just keep trying it until it actually gets to work. That's how I did it. How the data is shifted out, which bit comes out first, either the least significant or the most significant bit comes out first, either D7 or D0, and that's determined again by the device that you're talking to, and then you can set that up in the microcontroller whichever way works. And it's called the data order, or most significant bit first or least significant bit first. So now taking a look at the Atmel datasheet for the ATmega 328, just go down to the SPI serial peripheral interface table of contents here, and go through it very quickly here. This is what's actually in the microcontroller. It's a little more complex, but here's the shift register, and the data going out, and the data coming back in. The clock is generated by the CPU clock, the 16 megahertz crystal or whatever you happen to be using, and yeah, I'm not going to go through too much of this. It's really irrelevant here. These are the I/O pins that come out. The microcontroller can be set up to be a master or a slave, and for the purpose of this video, I'm only going to show you how to set it up as a master. I may do another video down the road where I show you how to set it up as a slave device. Oh yeah, this is what I tried to explain with my simplified drawing. So this is this is the slave device here. This is the gap between the two, the data lines. This is the master device. Clock is generated here in the master. It goes to the shift register in the master, also comes out and goes over to the slave and becomes the clock for the slave register. The data shifted out of the slave goes into the master, and what's shifted out of the master goes into the slave. This big loop that I talked about before. Definition of the pins, some little code examples to help you out. The slave select pin. The microcontroller can be set up as a slave device, and it has its own slave select pin. And you've got to handle this pin correctly if you're in master mode, because if the pin is an input and you pull it low, suddenly the peripheral device, the SPI device, will switch over into slave mode, and then you'll screw up. Your software is not going to work. So what you need to do is on this pin, and it's defined, one of the pins on it, on the microcontroller, is this pin. You just define it as an output, and if you use it, you can, and then that allows you to use it for anything else that you want. In fact, I often use it as the slave select pin for the slave device that I'm playing with. But it must be left as an output, so you can't mistakenly put the microcontroller into slave mode. This describes the 4 different data modes that I talked about already. There's another drawing, basically what I did. And then the registers. Let's just quickly go through the register. So this is the control register. It's used to set up your interface to make it work properly. You have to enable it, so SPI interrupt, or not interrupt, yeah, enable. This just turns the peripheral on. You have to set it to 1. It sets up, or on reset, the microcontroller sets this pin to 0, or this bit to 0, so the SPI interface is not enabled when you first power up. You have to actually initialize it and enable it. Oh, sorry, I didn't read this. This is the interrupt. This is the enabled bit for the peripheral. If you want to use this in an interrupt mode, which I'm not going to talk about in this video, you have to set this bit so that it enables the interrupt. But we're not going to do it this way. The data order, again, this I talked about which bit comes out first, the least significant or the most significant. It comes up from power on reset in the least significant or the most significant bit first. It can be switched around by writing 1 to this bit to make it least significant bit first. This tells the peripheral to be a master or a slave, but remember, if the slave select pin is an input and it goes low, this bit will automatically be set to 1. I think it is. That will make it into a slave. Or sorry, it would be 0. What am I doing here? This bit selects master SPI mode when written to 1. Okay, yeah, it has to be 1 to be a master. So you got to set this one up as well. So this bit here, clock polarity, in conjunction with the next bit, the clock phase, sets up one of the 4 different data transfer modes. And I believe it didn't do that here. I thought there was a table that showed you which bits are what to get which mode that you want. The final 2 bits in that register set up the clocking frequency, and generally most slave devices can clock at an incredibly high frequency, so you can transfer data very quickly. So I generally set it to FOSC, which is your main oscillator, the 16 megahertz oscillator in the case of an Arduino. I set it to the fastest, so FOSC divided by 2. It'll clock at 16 megahertz, or 8 megahertz. The status register, probably not really, you're really going to need to work with this one. If you do everything right, you won't get a collision. And this one here is a double speed. Yeah, this I think is unnecessary. You just leave it alone. Finally, the data register. So when you want to write something out onto the SPI bus, you have to write to this register first and then start the clocking process. When you want to read from the SPI bus, you still have to put something in here to get it to clock, because it won't clock any data out unless there's something in here. And you just put a dummy byte in here and then read back out of here. Once you've done the transfer, then you can read out of this data register what was clocked in from the slave. I'll show you that in the code. So that's it. There's only 3 registers that you have to play with in this device. And when I have a closer look at the software, I'll show you how these registers are used. So now this is the software for the SPI version of the same display. It's pretty much the same as for the I2C, except that the display has to be initialized a little bit differently. Also include the SPI bus as well, SPI code. Everything's the same. This is the main function. All of this is the same. You have to initialize I2C bus again because we're using it for this time for the sensors, but not for the display. And then this is initializing the SPI interface. And I'll go into more detail in a moment. We'll look at the SPI stuff separately. This is the same as in the previous version of this software. You just have to initialize all the sensors. And here this will be a little bit different. We have to set up the display using the SPI instead of the I2C, but the graphic stuff is the same. And then the initialization of what's on the display is the same. You notice the functions are all the same. The only difference here is this function here, which is instead of I2C graphics update, this is going to be SPI graphics update. And then in the repeated while loop here, everything is the same except for one function, which is here. We updated the display using the SPI bus instead of the I2C. So the code is very much the same in this part of it anyways, and the differences with the SPI bus is included. So let's look at some of the SPI code here. And there'll be, I'll have a link in the description below the video that will direct you to my GitHub site that has this code in it as well, including the SPI stuff. So let's see, SPI init. Basically, you just initialize the two control registers, the control register and the status register. And when you do that, let's look in the code here. So the first parameter is what gets written into the control register. And so these are all the different bits for the different modes and whatever. If I look at the .h file here, let's see, how do I do this? So these are all the defines for the control register. So this is the interrupt enable bit, this is the SPI enable bit, which turns the SPI interface on. These two set up the data order, 0 or 1. These two tells you whether it's a master or a slave. These four set up the different modes, the 4 different modes. These 4 are for your division, the clock dividers, to give you the clock speed. So the main oscillator frequency is divided by these values, and the same. These same ones are these are the same bits again, but if you set the SPI 1 times or the 2 times bit, depending on which one. So these 4 here require the SPI 2x bit to be set. So you would have to write this one in the second control register, or they call it the status register. And these are all for the first, not for the first register, but for the control register. And then there's the 1 bit in the status register you have to set up, which determines whether you double the clock speed or not. And so if you double the clock speed in that by setting the bit in the status register, then in the control register you'll have to use one of these defines. If you haven't set the bit in the status register, the clock double, then you can use these here. So anyways, to set up all the bits in the control register, you just pick one of each of these defines and just OR them all together, as I've done here. And that assembles a byte with all the proper bits set. And then the second parameter for the init routine is just the 1 bit, the 2 times register, or the 2 times clock speed in the status register. So that's how you initialize the SPI bus, the SPI peripheral. And so the 2 parameters come in here, and then they just simply get to the written to the appropriate register here. This is the slave select pin of the microcontroller. This just explains what's going on here, and that's what I'm doing here, is setting up the slave select pin, and also the clock and the MOSI pins. They have to be set to outputs. You just read through the code, the instruction or the comments there describe exactly what's going on. I've got a function here. This just turns off the SPI interface. If you need to change the bit order for some reason, this function will do that, and you just give it a code here. Where are we? Either this one or this one, depending on which direction, which order you want the bits to come out of the SPI peripheral. This function here sets the mode, so that's the mode 1 or mode 0, 1, 2, and 3, the clock polarity and all that kind of stuff. And that would be one of these numbers here, and you just pick one of them and put it into this function, and it'll set up the correct mode for you. And this is what I had to use in my project, that I had 2 different SPI devices, and they had different modes, and I had to keep calling this to switch the mode of the microcontroller back and forth. This function here just sets the clock rate, and again the speed is just that 1 bit, the SPI 2x bit, which gets set up in the status register. And the rate is, what is the rate? How do I do it? Oh, it's just these bits here, I believe. Yeah, it's one of these 4 defines, or these 4 here. So this is the heart of it when you're actually doing some data transferring. So you have to call this repeatedly, once for every byte that you want to transfer out or read back. And all it does is it takes the parameter and puts it into the data register of the SPI interface, and then the SPI will immediately start clocking the data out. You don't have to do anything else, but you have to wait until the SPI is finished, and this is what this while loop here does. It simply waits until the SPI has done its thing, and then you simply read the data register and return it with this function. It's really quite simple. As indicated here, this function will block for as long as the SPI interface takes to get the data transferred out. So the slower the clock speed that you use, the longer it's going to take for this function to return. So remember that. This is going to tie up the microcontroller until the SPI bus is finished. You can take this code and do it yourself, write an interrupt driven system. That way you can write out a bunch of bytes that you want to transfer into a buffer, and then have the interrupt system take care of that. But you'll have to write a bunch of software to do that, and I haven't done that in here. Simple function just to enable the interrupt if you're going to use it, and then also another function that will disable the interrupt. So that's about it. It's pretty simple. Like I said before, this is my way of doing it, and that's not necessarily the best way of doing it. But this code will be available for you to have a look at and play with and do what you want with it. So that's about it on the SPI bus. This is what it looks like. Of course, it's the same as the one I did for the I2C bus. But if you look closely at the display here, you can see there's quite a few more pins than the I2C. I think there's only 4 pins on the I2C display, and there's obviously quite a few more there. So that's the video on the SPI bus. It's not that difficult to use. I think most people actually find it easier to use it than the I2C bus. But either way, it's a very effective way of transferring data to another device. It is way faster than the I2C bus. If you've got peripherals that require a lot of data to be transferred back and forth, this is the way to go, because it's so much quicker. I'm doing it at 8 megahertz here, which is the fastest that the microcontroller can do. But I've worked with other microcontrollers, and you can clock things at I'm not sure what this display is rated at, but other peripherals can take data at 20, 30 megahertz, and so it doesn't take long to transfer a whole bunch of data to something, or read data from some device as well. So I hope you enjoyed this video and got something out of it. Go through the code and try to figure it out. I don't think the code is that complicated, and I put lots of comments in there, so you should be able to follow through. and then start playing with it yourself and learning how to do it. Thanks for watching.